Thank you. My name is André Santos. I'm a graduate student from the University of Lisbon in Portugal, and I'm here to present my master thesis paper named Monte Carlo Research Experiments in Arson, where the main goal was to build a game agent for Arson. We was using Monte Carlo research methods. So this is the presentation's outline. I will start by supplying some of the background, motivations, related work limitations. Then I will move on to show you my solutions, my adaptations to Monte Carlo research, as well as some of my experiments that I used to improve my approach performance. And I went with the results and some of the main conclusions. So, motivation. Why did I choose a game like Arson as my testbed? Arson is a collectible card game between two opponents. In terms of AI characteristics, is an adversarial game between two opponents. In addition, Arson is also a stochastic game of hidden information. So, as we can see in the video, both decks are initially shuffled in the beginning of the game, and the deck I can really see the data that my opponent is currently using. So this is the hidden information element of Arson. So indeed, I want to choose my main motivation in choosing Arson as my main testbed was indeed the AI characteristics and challenges that a game like this comes with. And why did I choose an algorithm, the famous algorithm Monte Carlo research, for building my solution? Because Monte Carlo research was recently applied in similar domains and with promising results. As an example, the game of poker. So regarding the paper contributions, we have mainly two. We solved the hidden information problem of Arson, one of the main challenges in building an EA for Arson, and also we deal with the large branching part of Arson by integrating expert knowledge in the algorithms in the Monte Carlo research process. So in this presentation, I will try to answer this main question, this main motivation. Will the integration of expert knowledge in Monte Carlo research improve the performance? I want to show if we integrate expert knowledge in the standard approach of the algorithm, we indeed come in improving the performance. That's my main, the main action, my main motivation. So, related work. At the moment that I was doing my research, different works, different studies in the literature have studied different aspects of card games, such as deck building, card generation, predicting the opponent's decks. One amazing paper that was also presented in the last year of SIG. So, but for the domain of general gameplay, the use of algorithms like Monte Carlo research has really become a standard in game EA. And why is that? Because we can already apply an algorithm of Monte Carlo research to games that can be represented as a tree, like Arson. So there are many developments in or AIs that use it Monte Carlo research. But at the moment that I was doing my research and the projects that use it Monte Carlo research for Arson, that apply Monte Carlo research for Arson, was never introduced expert knowledge to improve the performance of the algorithm, and was never solved the hidden information problem of the game. So these two main limitations at that moment that I was doing my research function as my main motivation. I wanted to really solve these two main limitations, and I tried to. So we now the approach. We already have seen the two main challenges for building an AI in Arson, which are the large branching part of the game, as well the hidden information problem. I can see the cards that my opponent is using, so I can't really apply the standard approach of the Monte Carlo research. So to answer these two main challenges, I propose a series of adaptations to Monte Carlo research where I integrate expert knowledge of the Arson in Monte Carlo research in two main forms. First, I propose the development of a platform of DEX database for us to be able to deal with the hidden information problem. And also, I propose the development of a heuristic function to guide the Monte Carlo research process. Um, these are our two main contributions. They are two main components. One little thing. Um, we all know that building a bot or AI for the official game of Hearthstone is illegal. So in my master thesis, I use it an open source simulator, widely well known in the community, named Metason, for me to be able to present my work. So let's now move on and give a brief overview of the algorithm Montcart research. Montcart research is a family of search algorithms that uses stochastic simulations for building a tree in memory from the current state. Um, the main behavior of Montcart research, the algorithm behaves within iterations. With the increasing number of iterations, we indeed have more nodes in the tree. We indeed have more knowledge about the environment and the current state. So each iteration behaves within 4 steps. First, we select one node from the tree. Then after the selection, we expand the node from the tree. The next step is the simulation process, and is the most important one. And the simulation process aims to produce an estimation of the current expanded node value. In the example, we indeed perform the simulation from the current expanded node value, and we concluded that this state is very bad. So the outcome, the fitness was 0. So the last step of Montcart research is to backpropagate the, the value 0 up to the root node for the game tree after the iteration always being updated. So one more important little thing in the literature, these two these 4 steps are commonly named as policies. When you are selecting a node or when you are expanding a node, these two main steps are commonly named as tree policy. And within the default policy, normally the default policy is also well known as the simulation step. So this is other terminology for the 4 main steps of Montcart research. Okay, I already have supplied a brief overview of the Montcart research algorithm. Now let's see my main components, and now let's study how the DEX database was used and the main motivation. So the main motivation behind the platform of DEX database was indeed for me to be able to solve the hidden information problem. Indeed, the DEX database enable us to solve the hidden information problem, for me to have a clue about the current strategy that my opponent is using. So how does this work? From the history of plays of my opponent, I will search across around all the database, and I will select a deck that is compatible according to the previous history of plays of my opponent. Let's suppose that my opponent already played the card A, B, and C. So I will search across around the deck's database, and I'm going to select the deck that also has the cards A, B, and C, or the deck that is the deck that have the most common reference of the cards A, B, and C. Another important thing is that at the time that I was doing my research, the deck database represented the current state of the art of deck strategies for Hearthstone. Indeed, I selected the most playable decks at that moment, and I built my platform of DEX database. That's the main motivation behind the DEX database, is for me to be able to deal with the hidden information problem, for me to be able to perform the default policy in Montcart research. Now let's move on to the heuristic information. Again, what was the motivation behind the heuristic information? For me to be able to deal with the large branching part of the game, for me to be able to guide the Montcart research process. In my work, I use it 2 types of heuristics. We have heuristic number 1, one that I developed from scratch, and actually that represented a concrete strategy in Hearthstone. And also the Metason, the simulator, was already built in and as a second heuristic, the heuristic number 2, that was indeed very good, and that represented a more general approach, more general strategy for arson. So during my experiments and during my results, my main goal was to try to figure out which one of these two heuristics was better for me to use the best heuristic in my adaptation to Monte Carlo research. So, and where did I integrate this knowledge, this heuristic information? I integrate in both policies of Monte Carlo research, in both the tree and the default policy. Or rather, when I'm selecting a node from a tree, or when I'm performing the simulation step. Okay, in the tree policy, I used an algorithm named progressive bias that was especially built for this purpose, for integrating expert knowledge when you are selecting a node in Monte Carlo research. In the default policy, I adopted an selection method of genetic algorithms named Torment selection method for me to be able to deal with the large branching factor and insert the current or insert some expert knowledge in the simulation. So the idea behind the tournament selection method is as follows. I randomly select kappa actions from the available ones, and I select the action with the best heuristic value if you are in a Monte Carlo research simulation node, or I choose the action with the worst heuristic value if you are in an opponent's simulation node. My idea behind this development is for me to be able to treat players as rational. This is my main motivation. Okay, regarding the value of kappa, the kappa value is very important. If we choose to use a value of kappa too low, perhaps kappa equal to 1 or 2, we cannot, the resulting default policy maybe is not inserting the current amount of expert knowledge for us to be able to deal with a large branching factor. But otherwise, if you use a value of kappa too high, perhaps the resulting default policy becomes too greedy. So that's a problem. And in my experience, I perform a series of tests for me to be able to deal and to study what's the best value of kappa to use. Okay, this is my two main contributions, or two main components, the heuristic information and the DEX database platform. But I also performed other optimizations to Monte Carlo research, where one that I named search tree reuse, and the main motivation is for me to reuse the previous tree knowledge in the building of the new tree. Okay. In other words, a turn in arson lasts 75 seconds. So within these 75 seconds, I can perform multiple actions. Perhaps I can play the card A after the card B, and then I may end my turn. So in terms of adaptation to Monte Carlo research, I start a new plan, the plan ends, and I return action A. Then I start a new plan from scratch, the plan ends, and I return the action B. But there's a problem. In the different instance of Monte Carlo research, I always started a Monte Carlo research from zero, and that's a huge problem because I lost the previous information, the previous tree knowledge. So I performed some experiments for me to be able to continue the search, to reuse the previous tree search in the previous tree. And the last experiment that I conducted was I studied 4 different methods to select the candidate reduction in Monte Carlo research when the planning is over. So, in other words, what is the best metric to use after the planning is over? Is the number of visits, is the number of victories, is the number of visits and victories, and so on. This is the purpose of the final action selection experiment. Okay, finally, the experiments. What's the motivation behind my experiments? I performed a series of adaptations to Monte Carlo research where I use tons of variables in use. So I really want to optimize my Monte Carlo research adaptation. So that's my main motivation behind my experiments. I performed a series of independent tests whether the parameter that I'm currently studying is changed while all the other ones are fixed. For example, if I'm currently studying the impact of the number of iterations in my Monte Carlo research adaptation, I gradually increase the number of iterations while all the other parameters are fixed. So that's my approach to perform the improvements and how to execute my experiments. This is the final parameters that I found and that I use from now on. Some little observations. With the increasing number of iterations and the increasing number of rollouts, indeed, my Monte Carlo search performance also increases, which is normal. With the increasing number of iterations comes with the increasing number of nodes in the tree, so we have more knowledge to work. Regarding the value of kappa, I found that the values between 50 and 75% were indeed the best. Regarding the heuristic information, I found that the heuristic already developed in the Metason, in the simulator, performed much better than my own because indeed integrated other metrics and a larger number of metrics. As another observation, I found that the number of victories was indeed the best metric to choose when the Monte Carlo research is over, and after the planning of Monte Carlo research is over, we need to return an action from it. So the best metric to choose is the action with the most number of victories. And yes, and finally, the search tree use, where when we continued the search from the previous tree, was also a good approach and a good optimization. So the results. Okay, how did I perform my results against all the different AIs in the simulator, in the Metason, and by using different decks? In Arson, the deck that we are currently using is very important. If I use a deck of type A, the deck type A perhaps it can be compatible with the type B, but not compatible with the type C. So that's why I choose to oppose different opponents and also different decks. But this approach wasn't really enough. I really wanted to see my improvements, the improvements of integrating expert knowledge in my bot, in my AA. So I create a second approach, a second Monte Carlo research approach that really doesn't not use any expert knowledge. The second approach, I name it Vanilla Monte Carlo research version. And the idea is for me to be able to compare and see if indeed the integration of expert knowledge improve the performance of my approach. So against the two worst AIs in Metason, the results are very clear. All the approaches, approach number one in blue, it's indeed my approach, and the bar in yellow is the approach is the second approach, the approach that doesn't integrate any expert knowledge. And as you can see, both approaches performed a win rate close to 100%, which indeed is normal because these two opponents were very bad. The random agent is an opponent that returns actions by random, and the no aggression agent is a player that really plays no physical attack actions, that doesn't attack the opponent. So that's the reason behind the performance of 100%. Okay, against the greedy player, a greedy agent is a myope agent that choose actions according to the heuristic value. We have a different situation. Okay, we have here three graphs that represented different strategies, and the blue bar is always my approach, and the blue bar is always paired with a second bar, the approach number two. Okay, we have the blue bar, my approach, and the second bar, the Monte Carlo research version that doesn't integrate expert knowledge. And as we can see in all the graphs, the blue bar is always superior to the orange bar, which explains that the integration of expert knowledge indeed improved the performance. That's why I wanted to pair both approaches for I to be able to see clear the improvements of whether integrating expert knowledge or not improve the performance. So let's see some numbers. In average, my approach presented a win rate of 61% in average, but the second approach, the approach that doesn't integrate expert knowledge, presented a win rate of 40% in average. So, which indeed represents a gap of 20% between two approaches against the different decks that we are using. Okay, against the more strongest opponent in the simulator in Metason, we have similar conclusions. In average, my approach presented a win rate of 42%, but the second approach presented a win rate of 21%. Again, a gap close to 20% between two approaches, which indeed explains that the integration of expert knowledge indeed improved the results against the different opponents, against different strategies, and against the different decks. That's why the reason of so many graphs. Indeed, the blue bar is always superior against the orange bar. That's what I'm trying to explain. Okay, conclusions. Hearthstone indeed is a challenging game. Two main challenges: hidden information problem, a large branching factor. So I found out at the time that Monte search is a valid alternative. So what I performed, I integrate heuristic information in the tree policy and in the default policy, and I also solved the hidden information problem by a platform of text database. So regarding the initial question in the first slide, will the integration of expert knowledge in Monte research improve the performance? And by the experiments and the results and all the graphs and all the bars, yellow and orange, we can see that yes, indeed, the integration of expert knowledge improved the performance. Okay, that's it. Thank you.
Of course, the knowledge-based piece, the vanilla, yeah. But do you have, you don't show out the numbers, but do you have which part of this knowledge-based contributed the most? Like these decks are, yeah, like, you know, this some winning percentage decks is enough to.
Yeah, I understand.
The other parts, yeah.
The most the answer is the heuristic information. Indeed, the heuristic information enable me to guide the selection and the simulation strategy. The heuristic information indeed guide me to the two most important steps of Monte research. That's the reason why the heuristic information is the most important part of my approach and my component. That's the heuristic information, the integration of the heuristic information in Monte research.
What's your thing about that? You have some this AI with heuristic information and with heuristic information and, for example, this deck, you know, trying.
Yes. Okay.
Last question.
Just a comment in relation to what the previous question I said. I think it's not always obvious that adding expert knowledge will improve it. Indeed, there were some quite famous papers that really questioned it and said you had this thing that by increasing the bias of the search, sometimes you could actually deteriorate performance. So it's interesting to see in this case. I actually believe that it is done correctly and nearly always does improve performance, but it's quite good to see that it did. How expensive is it to apply the expert knowledge? And did you make tests also where you keep the time limit the same?
Okay. About the, let me see. The first time ever that I was able to implement the standard version of Monte research, the average time for my approach in returning a single action was about 2 seconds. Okay, Monte research average in 2 seconds for returning a single action. After I integrated heuristic information, the average time increases almost exponentially to about 15 seconds, which indeed answers your question. The heuristic information indeed improves the performance, but also increases the computational time. That's why in my experiments I try to figure out a good configuration of parameters that between a good performance and also good computational time. That's my main goal of my experiments, to find a good configuration between these two main values, the time and performance. That's what I want to reach at that moment.
Okay.
Next speaker. And the second speaker of today is Rui
Yeah. You want to bring up your presentation? No, I don't need these after. Do you want to just show? Yeah, this one.
Yes. Floor is all yours.
Thank you for the introduction. I am a PhD student from Brazil, actually studying in Fortaleza. We are working in a research group that focuses on ubiquitous computing, pervasive games, and in my case, location-based games. And today, the focus of the work I'm presenting is location-based games. And these games, which are now really known because of Pokemon Go and Ingress, we have been working with them for a while. And they are games who usually, who needs to use most of the time track the location of players to modify the game and progress and change their state. And usually these games, especially these more recent games like Pokemon Go and Ingress, they use this database of points of interest to map real parts of the world to virtual points in the game. And the players have to move between these points to interact with them and to progress, and that's the fun part of the game too. So you have this combination of need to move between these points that make the link between virtual and real world. But we have some great challenges when developing these games, especially because it is very hard to make the games available everywhere. Eventually, either we will have to rely on some algorithm to do it, or in the case of the studies, I've made a community-based effort to implement the game in multiple places. But also another great challenge is the game balancing. So in these cases, a lot of players have complained about this issue. And especially in Brazil, I mean, in New York, you probably won't have this problem, but in Brazil, there are certain areas that we don't have points of interest, or you have just a few, and it is unfair when you're competing with someone else, even if it's in the same city, or if it's in another city or in another country. So it kind of harms the playability and the fun of the games. So these are the main challenges, and we've decided to address them. But first, we have to understand what is game balancing and how we can treat them in location-based games. So game balancing is related to the difficulty of the game. So in a nutshell, a really hard game is going to be frustrating, and too easy games will be boring. So we have to kind of figure out this golden range where it's fun, it's not boring. And it is crucial. In modern games, we have seen a lot of papers working on it, using artificial intelligence to set up, to calibrate, to make it perfect in terms of game balancing. But it's a really hard task. It takes a lot of time. You have to test it a lot. So game balancing in location-based games is even harder because you have to address many other issues like terrain topology, the availability of transport for people to move depending on the game, public safety, weather. There are a lot of stuff that will make a game really difficult to play depending on the area. So this complexity grows exponentially. In fact, to estimate this difficulty level, we had to make some adaptations, of course. and we've decided to represent these games as a weighted graph. So the effort to move between these points of interest will define how hard or how easy the game is. So we just made this direct mapping where each node will specify a point of interest. Each edge will be an existing path that a user or player can take, and the weight will be any measurement you consider valid to evaluate the effort to go along these paths. And we usually will attach some feature, some measurement to the weight. Depending on the game, it may be time, it may be distance, footsteps, heartbeat, if it's healthy game, if it's, I mean, depending on the game. So this will be our approach to measure the game balancing. And we've came up with two measurements to evaluate them. First one is the internal difficulty level. It will try to evaluate the effort to move within this point, within this area. So you're not comparing one game with another. You're not comparing two cities. You're just evaluating if in that place you'll have two easy points or two hard points. So we kind of focus on analyzing the average cost to move and the standard deviation. And the second measurement is what we call minimum balancing difference, which will try to highlight the difference between two games. So this one is interesting when you try to make a competitive game, to play multiplayer games. So it will define the minimum difference considering these both graphs. Now the games are represented as graphs, so we kind of we have to just subtract the weights from both games and see the minimum difference between them. So we will have a value that will tell us how different they are. So in a nutshell, this last measurement, if it's 0, it means the two games have no difference whatsoever in any path between them. They are just the same. User will have the same effort to move between points. So it will be 0 would be perfect comparison between games. So our method was to change these points of interest to minimize these differences. So we needed to assess these many points, these points of interest, and this is a problem because you have a lot of candidate points of interest, and it will lead to huge search space depending on the number of points you have. It is a permutation of places, of positions, and this problem is well known. Is the graph submatch problem where you wanna where you have a smaller graph and you want to find a match, a suitable match in a larger graph. So it's a complex game, and we used MCTS to explore this huge search space and find the best solution. In this case, the MCTS will select the points of interest that are potentially better results under a certain budget, because it is very large. We have to limit it. And here you can see a picture showing how we've defined this game. First, in blue, you will see the original game. It's like you have a game, for instance, here in New York, and you're not really happy with it. Maybe it has some hard or really easy points, but that is a version of the game. It may be even a artificial version that we call target LBG, and this game is like the perfect one. You want your game here to be like that target game. So we'll feed those two games to our method. They will convert them to a weighted graph, and then select points of interest in the area of the original game. So There are some available points to replace the current ones. And then the Monte Carlo tree search will search for this combination of possible solutions and of points of interest to try to select the best one. And then we will analyze the improvements that have been made and output a new version of that original location-based game, but now it's improved to look more similar in terms of game balancing to the target one. How is this conversion made is just a direct mapping, the way I said before. And the tricky part here is to estimate the effort, because they are the most important part of the method. So we've used in this work, we've used Google Maps to estimate the distance or the time to walk between the points. And we've made an analysis using Pokemon Go and Ingress. So these two games, they kind of force you to walk. If you're driving, they will block you. So it makes sense to use distance or time to walk. But again, you could use any distance, any measurement. If it's a healthy game or anything, you can switch it for calories or other stuff. So we estimated it, and we also could put any other features to this effort. The MCTS will receive these graphs as input, and we will try to find, to search for matches that will minimize that measurement we proposed, the minimum balancing difference. And searching, in this case, searching for solutions will be the selection and expansion part of MCTS, and the simulation will be to calculate the minimum balancing difference. So to do that, we've defined a limiting threshold, a similarity threshold, to define if it's a good solution, is a fitable solution, or if it's not, so we won't have to go deep in that branch of the tree. So we've defined this threshold, and it's like a percentage of similarity. I mean, if it's 0, it means the games are the same, so you will be a perfect match. And the algorithm will go through the solutions that are under this threshold, and in the end, after you've given the algorithm a certain budget, it will output this solution with the better difference. In this case, the lower minimum balancing difference. So to evaluate, to analyze the method, we've used both Ingress and Pokemon Go. In fact, they share the same database, so it works for both of them. And we've selected locations in different countries, mostly 2 places in each city, so we could evaluate the difference within the same city and also compare if it's fair to compete with other players from other countries. So we've selected 2 regions in New York, 2 in Tokyo, 2 in Rio, and Johannesburg and Berlin. And these areas we've analyzed, we've applied our method to improve the balancing. So now we have the first analysis we've made using the internal difficulty level. So you'll see in New York, the first bars, you'll see New York 1 and New York 2. They won't be, there will be no much effort. No, it's not really hard to play because it is quick, or is really, it will take you a short distance to go through the points. But if you go to some other cities like Johannesburg, or even some points of Berlin, you will have higher time and higher distance to cover all of them. And this the standard deviation also shows that you have some really different, really big differences in balancing within the same area. So here is an example of Berlin. in this BL2, you will see there is a red point up in the picture. So it is hard for players to cross that river. That's why the standard deviation is so high, because you have this point that will take them to all the way across, take some bridge to reach that point. And our method will replace that point, because it will lead to bad results, great difference between them. And we'll replace it with another point inside that small area, which is like an island. So these kind of problems will be solved when applied our approach. Here you have a table comparing each city to from those 10 cities, comparing each one. So you will see some difference. I've highlighted in orange. For instance, 2 areas in New York, they have 40% difference. If you go to Tokyo and Johannesburg, you will see almost 90% of difference. And even Berlin, Tokyo and Berlin, more than 100% in difference. So here you can have a look and see that there is a lot of difference between the balancing in these areas. So let's focus on Tokyo and Johannesburg, which is 90% of difference. If you see, here's the picture. And on the top, here to the left on the top, you will see Tokyo, and below it, Johannesburg. But you see, after we applied our method, the bigger picture will show you how is the game now in Johannesburg after our method. And it is similar to the target game, which is Tokyo. So we are changing the game in such a way that it is so improve the game balancing in this case that it may even look like the other one, the spatial distribution of points of interest. And also the most important evaluation was to analyze this minimum balancing difference. So we will have the original game and they improved the game, and after applying it, we've the results were very good. We've managed to keep them in all cases below 45%. I mean, you had in some case over 100% in difference, and after applying the method, we've managed to keep it below 45% in all cases. So it really helped to improve game balancing. And to have a better idea of how the game balancing is working, you have in blue the original game, in green the target, and in red the improved original game. So it was really hard, and we've applied to a target game which it was easier, and the result will lead to a pretty close version of that original location-based game. So here you will see real, the points were shifted, they were replaced to look like to have a game balancing similar to the one here in New York. So the results were promising, but we have some limitations. The method won't suit any location-based game. Mostly we are working with games that use points of interest, and there are a series of games that don't use it. We also may have to improve the matching between real and virtual points, because depending on the game, you want the virtual point to, if it's a store in real world, it will be a store inside the game. So we didn't really make anything in the algorithm to make sure it will happen. Depending on the case, it may even replace all the points, and it may not be something you want to. So we haven't yet figured out a way to hold some points. It is not hard to do it, but we didn't do it for this work. And we also have to analyze the threshold because if you set a really high threshold, and any match will be good, so the algorithm won't work. The same thing will happen if you have a really high threshold, so every test, every solution will be like a loss, and Monte Carlo tree search will backpropagate always lost, loses, so it won't work as well. And also the game balancing is not adjusted for real time. I mean, we get the time before, we estimate time and distance before using it, and if it change while you are playing, we are not considering updating the game balancing. So to wrap up, game balancing in location-based games is a open challenge. It's real hard challenge. Our method uses Google Maps to estimate and improve game balancing. We've used MCTS to select best solutions under a specified budget. The results indicate a promising approach, and especially when you have great differences. And in the future, we would like to improve the selection of points of interest, maybe matching them between virtual and real world, and handle more aspects. We've worked only with time and distance. Maybe we will figure out a way to use many other dimensions and define a better way to evaluate game balancing. So that's it. Thank you for your attention.
I was wondering, you were just looking at the distance between the different points, but I know in Pokemon you can cooperate if you're at a point of interest, but still, if you have much higher population density at some point, then you might not be able to use all the points of interest if you're too late, right? And then the density of the points doesn't really reflect how difficult it is. And in addition, you also have teams in both Ingress and Pokemon. And that's another complexity that isn't really reflected with the distances, right?
Yeah. In the end, it will eventually go down to the weight. So how to define the weight will have this impact. You may even consider the groups division to define if the weights will be higher or lower. And also, depending on the area, you may have a lot of points. In this case, we've analyzed the games using 10 points and selecting another 10 points of interest to be candidates. So of course we could have expanded the selection and have greater search space. I mean, it will grow a lot if you keep adding it. But it's definitely, it's initial work. I mean, we have a lot of other stuff to work on, and points you are saying they are valid, and we just have to keep working to find better ways to solve it. I'm not sure if I had answered what you were asking.
I guess, yeah.
Yeah.
Thanks.
Thank you. Oh.
Yeah, that one. Yeah.
Yeah.
No.
Yeah.
Yeah. Yes. Yeah. You reduce it quite a lot.
Yeah.
But I'm still wondering, is 45% okay? Is it good? Is it bad?
Yeah.
What would you like to have? 5%, 10%?
Yeah.
What is basically an acceptable?
Yeah. The perfect would be 0,
Yeah,
but.
But what is acceptable?
Yeah. We are planning on making real life experiments. Maybe put some players to play in certain parts of the city and evaluate if with 30%, 40% they will have a even match. but it is not great. I mean, the wonderful would be pretty close to zero. The fact is that these games are being released with very high really huge differences. So when you improve it, you are improving it a lot. I mean, depending on some cases, 3 times better. So it was so bad that any improvement will make it significantly better. But in my opinion, and I have been playing the games for a while, I believe it would between 20 and 15% will be good, because I've tried it myself, trying to compare regions. But it also, let's not lose the focus of the weight. It reflects a reality of a place, but it's not the full reality. If you walk 30 meters here in New York in the winter, it will be different from walking 30 meters in Brazil in the middle of the noon. So these kinds of features are the most tricky part, because we have to find a way to put it all together in the method, and we will have a more precise and reliable measurement. Thank you.
There we go. All right, thank you very much. Hi, my name is Simon Demajuk. I'm from the Royal Melbourne Institute of Technology in Australia, and I'm here to talk to you about the work that we've been doing there on dynamic difficulty adjustment using Monte Carlo tree search. Now, this work is one small part of a larger body of work, so it'll help to give a bit of context. So what we're trying to do is figure out a way in which we can improve people's skills in either educational games or just game training or military simulation through just skill acquisition through games. And excuse me, this one part of the work, which is presented in this paper, is a small but integral part of this overall thing. And I'll give some more context on that at the end of the talk. So the motivation behind this work itself is really to tackle the issue of game immersion. So, a good game is one that's immersive. People will play games that are immersive. And one aspect, and this is not the only aspect, but one aspect of game immersion is having a challenging opponent or a challenging environment. And how do we give the right level of challenge to an individual player? And how do we, how can we set a challenge level that everyone's going to enjoy? So we've really been motivated by looking at competitive play and how some people are relating, the best challenge is, an evenly matched opponent. It's been the basis of ELO for a long time, and there has been some research to say that yes, the most challenging opponent will beat you half the time. So we were inspired by that work, but what we have in the standard era is this concept of easy, normal, and hard difficulties. So when you start a game, you're usually asked to select from one of these difficulties, and generally, if you haven't played that game type before, or you're not really sure of your skill level, you'll pick one and you'll play through, and either you'll get better or it'll be too hard and you can become frustrated, bored. These are the types of issues that you get with the standard method of doing things. So what's been going on for a while now is this concept of dynamic difficulty adjustment, where we get rid of this easy, normal, hard sort of concept, and we move into this thing of a challenging level. So this can either be a challenging opponent, if it's a direct opponent game like chess, or a challenging environment game. If you're just exploring an environment, the challenge is set by your skill level. So as you improve, the challenge improves relative to your skills. So that's the focus of what we've been trying to tackle with this work. Now, the research that we've been working on has been in the fighting game genre. So the fighting game engine that we use is the Fighting Ice one that's used here for the competitions. It's similar to Street Fighter and Mortal Kombat, where you take control of one character and the idea is you are trying to beat the other person up and reduce their health to 0. Use a series of actions, kicks, punches, that sort of thing, to try and achieve that. So in terms of dynamic difficulty adjustment, this has been tackled before by a group about 8 years ago, and they developed a method called challenge sensitive action selection, specifically for this fighting game genre, but with wider applications. So essentially how they developed their system was they took a reinforcement learning approach where they did some offline learning, they built the value functions, and they basically listed all the actions for each state, and they gave them a rank based on the outcome, based on the reward that each action relates in after it's gone to the next state. And to achieve this dynamic difficulty adjustment, they choose the medium ranked action to start the game with, and after a number of cycles, they reevaluate the player's position, and then they either bump that rank up to choose harder actions, or they drop that rank down to choose easier actions. So one of the main findings in their work was in this specific genre, they claim that an evenly matched game is one where the final health outcome is between plus or minus 10% of the 0. So if you win or lose with about 10% left on your health bar, that seems to be where the ideal level of challenge for opponent in this genre is. And so we've taken this work and we're working from that. Some of the limitations, however, on their work is you end up with this problem of slow ramping. So what they found that is if you ramp up or change the difficulty too quickly, the AI behaves irrationally and it doesn't feel great for the player. And another problem with this method is there's a lot of fine-tuning of the parameters. So especially with the ramping cycle, as well as all the parameters that come along with reinforcement learning to get the value function correct. So we took an approach using Monte Carlo tree search. So we've heard a lot about Monte Carlo tree search. So I'll just briefly touch on how it works. We have these. You build this tree through these different phases, and then once you've got the tree and you figure out what the best action is, you pick the best action. So the traditional Monte Carlo tree search method usually uses most visited or most victories for the best action. Our method is sort of unconventional in the fact that we don't want to do that. We don't want the best outcome. We want the outcome that provides the most challenge. And just in our simulation phase, how we simulate this first body of work was actually just using sort of random actions, so people taking random actions in real time to build the simulation. So our agents that we started with, we're going to call them Rosis and Posis. They've got very catchy names, which is good. The first agent, we wanted to see if we could get an agent to sort of play better than the plus or minus 10% and actually just react every time you take health off your opponent. He's going to take the same amount of health back using different moves. So if you perform a large combo and do a lot of damage, it's going to have to do a lot of work to get that gold back, but it's going to keep the health relatively close to the 0, the difference. And then with that agent, it kind of doesn't feel great to play against because it's only punching you back when you punch it. So we took the other approach with the proactive version, where if we actually target the range of challenge that was defined earlier, we can actually get the agent to sort of initiate a small lead on the player, and also sometimes play more passively depending on the game situation. One of the so one of the problems with this is it doesn't actually take advantage of what Monte Carlo tree search is good for. And Monte Carlo tree search builds its trees asymmetrically. So it is focusing on the victories when it's building its trees. So a lot of the interesting area when it's building these trees is in these victory conditions, and that may not necessarily give us the best indication of what our actions are going to result in, because we haven't explored those trees to any greater depth. So we updated our agents, and we're calling these true versions of these agents. But what we do is, instead of just choosing the action at the end based on a standard Monte Carlo tree search, we actually change the heuristic strategy for building the trees. So in the reactive case, we build the search tree actually with, instead of a victory in mind, minimizing the health difference between the two players. And then similarly with Rhosis, we do a weighted around the zeros. So plus or minus 10% around that, and then we choose, and then we give them all the same value in terms of the node score. And then when the tree's finished, we can just pick the best action because the tree was built with the agents in mind. So in order to test, how these agents work, we conducted a small experiment that was presented in this paper. We've since expanded that experiment, but I'll talk about that only briefly at the end. So what we've got is we've got our 4 agents that we've developed, and there's some competition bots that were submitted by students in previous years, and we took a selection of a few of those that we thought worked the best. And there's a random commands bot in there just to ensure that we're actually doing what we want to be doing. And then we played them against a couple of human players to see if we got the same results with bots that we ideally want to get with humans. We've since expanded it right to include all of the competition bots from last year, and expanded it to 35 human players recently. So the bot trials. So to conduct the bot trials, we played 500 games of each agent versus each bot. And each game is 3 rounds, 90 seconds, and they all start with 500 health. That's just more a percentage thing. So when we talk about the plus or minus 10%, it's around the 50 health point mark. Unlike a traditional game, it's not best of 3, so each game is actually 3 rounds. And we were not too concerned about who wins or who loses, but more about how the agents perform in adapting to each bot. And during the human trials, we gave the human players a couple of warm-up games against some of the competition bots, just so they understood the controls and how to actually play the game. And then we gave them one game against each of the agents. And so the results that we got were quite good. I should mention, which I failed to do earlier, is we've actually implemented the challenge-sensitive action selection in this engine. Their engine they used was a lot older, but we updated their method and gave it a Monte Carlo tree search backbone to build the decision tree rather than reinforcement learning, but their methods were still implemented the same way of ranking the actions and scaling them up. And what you can see here is, if we talk about the reactive agents first, you can see here that they are very close to the 0. So these are aggregated over all the games against all the bots. And you can see that the outcomes that they were targeting of the 0 health difference, they actually managed to achieve that quite well. And then if you look at the proactive ones, they have a range. It's not exactly plus or minus 10%, but it is a range around the 0 that's quite good. On the right here, you can see we've actually played the just pure Monte Carlo tree search against the agents, and it's quite capable of beating them. But one of the limitations that with this work is when you use Monte Carlo tree search to actually do the adaptation, the strength of your tree search is actually going to depend on if you can adapt or not. Because if a player can beat a Monte Carlo tree search pure player, you can't adapt to them because they'll have a level above what you're capable of achieving. So we've got some more detailed results here. We conducted some 2 one-sided t-tests to see if actually the results that we got were what we were expecting. And for Rosas, we can see that yes, they're playing. We're quite confident they're playing within 4% of the health differential, even though they're targeting the 0. And with the proactive versions, we're actually quite happy that they're targeting within the plus or 50 health range, which is the 10%, which is our target for a challenging opponent in this genre. We then moved on, so we did the human trials, and we got slightly different results for the human trials. The standard deviations were quite high, but again, this is only a very small trial with 5 players, and they only got to play each bot once. But they're reasonable. The means are within the ranges that we expect them to be. Again, it just gave us a bit more confidence in the fact that these agents were actually doing what we set them to do, which is to try and provide this challenging opponent. So in the extended human trial, so these are aggregated over all of the human games, we can actually see similar results to the box plot I showed earlier. So we played them against just the reactive agents and challenge-sensitive action selection, as well as pure Monte Carlo tree search, and the performance seems to be similar to what we're getting with the bots, which gives us confidence that our method will actually hold true when used against real human players. I've added some slides here that aren't in the paper, but they sort of just show the progression over the course of the game of how the agents are working. So in the reactive one, it's quite hard to see because it's quite well, but there's a black line in there, and that's basically tracking the 0. So that's the mean there, and then where the grey lines are sort of the standard deviations apart. So what you can see is time as the game progresses, it's doing its job. It's maintaining that 0 difference as time progresses. In terms of the proactive one, we get a similar result. We were expecting to see a bit more variation around the 0, but granted, to achieve the proactive, it's choosing a random action, so that range is going to be random, and if it's choosing one, in our case, every 4 seconds, you're actually going to end up, on average, very close to the 0 with this proactive agent. So what does that mean for the rest of our work? Well, so we've got this method for doing dynamic difficulty adjustment using Monte Carlo tree search. We've got 4 agents there. But how can we sort of improve on these results? And how do we more generalize this to different genres? So in the fighting game genre, you've got this concept of it's a short-term strategy, and it's in real time. But how are these agents going to perform when the strategy is more long-term? How can we guarantee that this sort of simulation of doing dynamic difficulty action actually works? So we want to look at adversarial simulation rather than random simulation within building the tree. But we also want to look at what is actually the most enjoyable level of challenge. So even though we use this concept that was established before of targeting a health point difference around the 0 end of the game, is that actually the most enjoyable level of challenge? Because from our results, we don't actually end up with a win rate of 50%. Well, we end up with a win rate more in the 30 to 40 range. So we need to really figure out, what people find enjoyable, and what people find enjoyable is going to be different. So there needs to be some sort of adaptation method there. So if people enjoy an even harder challenge, you need to be able to register that and increase the outcome that you're trying to match. And then the next challenge is obviously how do we get the right level of challenge for skill improvement? So when you're trying to get better, so let's say I want to become a professional esports player in Street Fighter. If I want to get better and better at Street Fighter, do I play harder and harder opponents? Do I start off easy and then ramp up the level of challenge that I want to try? What's the best level for learning? And then, the final question that we have, and a lot of this work is coming out later in the year, but how can we measure the skill level of players without players directly competing with each other? So generally, when you do ELO and the new one from Microsoft TrueSkill, you play players against each other and then you adjust their ratings. And we want to do that. If you're in a learning context, you might not want to play people online, so they don't know how good you're getting. So how can you actually measure how good you're actually getting without this direct competition? So that works just to put some more context on the work that we've been doing here. All right, are there any questions?
So thanks for the description of your current work. What I'm interested in is you're currently working on short-term decisions of what moves you are going to do.
Yeah.
I have the experience for my own, because I'm not a skilled player in fighting games, that I find a move that suits my playing style and then continuously repeat it. And this is not really challenging to counter, but is there any specific method you try to apply for countering strategies in the long term to really force the player to learn new playing styles or strategies?
Yeah, so that was sort of a bridge too far for what we were trying to do, because I guess I've thought about this question a lot, and what you really want to do if you want to teach the player a skill set, especially in a fighting game, is you actually need to model the player as well, and then base your actions that you select to force that model of the player to branch out. So if the player is stuck doing one thing, you need to force them to do something else. But we haven't tackled that in this work, but that sort of becomes this combination of building a challenging opponent, but also then building a model of the player that we can go, okay, we want you to have this broad range of skills. If you're focusing in one area, we have to change this level of challenge a little bit, and what we're actually doing in terms of actions to broaden your skill level across that board. But yeah, we've dealt with that, like that question's come up a lot, but we haven't actually looked at tackling it just yet, because it's a much larger piece of work.
Yeah, okay, I guess so.
Yeah.
Tom?
Oh, yep.
Multiple worlds.
You can go on next.
Thank you. So, how do I find?
I'm going over because PowerPoint is. It's not PowerPoint. Oh, it's just PDF. Ah, there it is. Oh, that's not the screen. Way at the bottom. No, not slideshow. Ah, oops. Slideshow, it moves on its own without your permission. There we go. Thank you. Okay, I'd like to thank the organizers for moving this talk from Friday 10 minutes before my plane took off to today. I apologize that it's not quite appropriate to this session,
but this is a vision paper, and it was actually sort of appropriate to several different sessions. It's joint work with my former student, Joseph Alexander Brown, who is presenting 2 of my papers in England this week at IEEE's Bioinformatics Conference, which was scheduled on top of CIG through some confusion over at the conference committee, I guess. So in a game, it's often the case there are multiple roles or types of actors with different goals. One possible target for automatic content generation is to create multiple different types of software agents for these distinct roles. And what I'm going to tell you about is one approach, the multiple worlds model. It's about half of Dr. Brown's thesis. And I'm going to demonstrate it on Prisoner's Dilemma because that's sort of my go-to super simple, easy game, but I think it applies a lot of places. Now, one of the first people I worked with was an electrical power engineer, and I worked with 2 of his graduate students to build agent-based models of the then newly deregulated electric power market in the United States. And each agent was actually tested in 3 roles: power generator, power transporter, and power distributor, and it was a meltdown, a disaster. It just didn't work. The trick is that those 3 roles are very different, and we really needed to encode and train the agents separately. So the key point was any fitness evaluation had a couple of agents of each type, because you got to generate power, you got to have somebody that gets it where it's sold and somebody that sells it. But we bred the agents. We applied the genetic operators for the evolutionary algorithm only within each type. And this original implementation was done in MATLAB by the graduate students with my advice. It's sort of clunky. And that was the last time we did much with it until Joey came to study with me at Guelph. And then we worked out this model where you have n types of agents, and each type has a population. And then the first one from each type forms the first world, i.e. a place where a simulation could take place because you have all the required types of agents. And so you get a bunch of different worlds, which is where we get the name. Fitness evaluation is across the rows, breeding is within the columns. Not hard. Okay, so each agent type has its own population and a role in the simulation. Fitness is estimated by running simulations with 1 or more agents of each type as required by your problem. Usually, you do multiple fitness evaluations. The agent populations, the vertical ones, are shuffled each time so that you're evaluating a given agent in multiple different worlds, and he can't get a high fitness just because he was standing next to people that can't compete with him. And then the role of the agents may be predefined, and that's the experiment I'm going to show you at the end of this talk, and it's the first time we've actually done that, because they can also be profitably self-organized. So the little red crosses there are a synthetic data set. What I did was I generated random X values and plugged them into one of 3 lines to get a cloud of points that has this very obvious structure that's they were sampled from 3 lines. But then what we did was we had 3 worlds. Each world had agents encoding a line, and an agent got credit for a point if it had the lowest error on that point. So what happens? Well, one population will start capturing more of the points drawn from one line, another will start capturing more of the points drawn from another line, and we very rapidly recovered the equation of all 3 lines. Now this is an idea we've used other places where you have multiple models. You check the error of each model on each point and award the point to the model where it does best. And you get this very weird phenomenon called partitioning regression, in which you're simultaneously modeling and partitioning the data. Those of you who walk in the door with, you know, a terabyte hard drive full of player data may be able to use techniques like this. Now, lest you think I've discovered something really foolproof and great, look at those 2 pictures. I sampled points from a parabola and a line. And on the left, I recovered the parabola and I recovered the line. No problem. On the right, and this was using genetic programming, not just a simple 2-parameter line, it managed to come down the parabola, go across the line and up the parabola, and then to come in on the line, go to the bottom of the parabola and go along. I still have 2 models, but they partitioned the model very differently using the if-then-else operators you get in genetic programming. And in fact, I had a whole talk that caused the audience of mathematicians to break up laughing at how many stupid ways this method can break up certain sorts of data. So this is what we've done with it so far: partitioning regression, locating biological motifs that classify DNA. Joey's pet project was trying to come up with radio playlists that would correctly partition a market of radio listeners with different interests. That one, though, I think he submitted it 4 times before he finally got it accepted, so I'm not sure it was a good application. And then simulating interdependent bacterial ecologies. That was one. So one of the problems we have in trying to understand disease is if you pick a random bacteria and try and culture it so you can study it, it doesn't grow. About 2% of all bacteria can be cultured. The other 98% can only live if there are other friendly bacteria around with them. And so what we were generating was populations of game-playing agents that played a game called the metabolism game that would simulate this phenomenon of having things that had to have their collaborators to play the game well. And it worked fairly well. But every single one of these, what we're doing is taking a single agent type and allowing the simulation to self-organize into different groups that are useful for our purposes. We never really got around to doing the original thing that we wanted to do for the power generating agents. So I'm going to try and do that with Prisoner's Dilemma. For those of you that may not know, it's a 2-player game. The 2 players have 2 choices of moves. They can cooperate or defect. And there are 4 possible outcomes. S, or sucker, means the other guy defected and you cooperated. You got stabbed in the back. Or you could both defect, or you could both cooperate, or you could stab the other guy in the back successfully. And we required that getting stabbed be no better than both defecting, be no better than both cooperating, be no better than stabbing somebody in the back. And also, the average of stabbing and getting stabbed can be no better than no better than cooperation. And this was like published in Science in 1981, and there are literally thousands of papers about it. So what we did was, instead of just having a mixed bunch of agents play Prisoner's Dilemma, we created 4 types. Type 1 wants to maximize its own score. Type 2 is like Le Fou. It's some sort of lackey agent, and what it wants to do is to maximize the ratio of the score of Type A agents to Type C agents. So it's trying to get A to have a high score. It doesn't care about its own score. C wants to maximize the ratio of its score to those of Type A. Anybody here remember what happened when they had undergraduates run a nuclear war in simulation? Anybody not familiar with that experiment? Okay, so what they did was they told the undergraduates their goal was to minimize the damage done during the nuclear war. Of 20 undergraduates that participated in the simulation, 2 of them, women, actually followed those directions. The other 18, 3 women and 15 men, tried to maximize the ratio of the damage. They wanted Russia to be blown into much smaller pieces than the United States, and they failed this was a test in a game theory course. They just couldn't understand. No, we want to minimize total damage. So C is playing like these testosterone-soaked undergraduates, and A is just trying to maximize its own score. Whereas D wants to maximize the average score of the agents of all types. It's just a nice guy. So these are 4 very different goals. And we got 4 very different behaviors. Red is Type A, they're trying to maximize their score. Green is Type B, they're trying to maximize the score of A over C. Blue is Type C, which is trying to maximize the ratio of their score to A. And D is the one that's trying to maximize everybody's score. And the only behavior I completely understand in all simulations is D, because what D does is it cooperates no matter what and lets everybody else defect against it. So it gets 1 really bad payoff and 3 other agents get really high payoffs. This is the correct solution for D. The others, and so, it doesn't come out the same all the time. The raw score is plotted, not the values used for selection. So these plots don't really tell you how the selection is going. And it turns out that the agents that are the Le Fou, lackey agents, actually do better than the we're out to maximize our ratio agents, because they very often help A by simply cooperating with it. So it's a little hard to figure out what's happening. This system could be used to design toadies to help your strategy in a contest. We've had these iterated Prisoner's Dilemma contests where people had Confederates submit agents whose whole goal was to identify the core agent and help it get a high score. And so you could actually, automate the design of this sort of cheating. And then you can also use it to study asymmetric payoffs. One of the things a colleague of mine has urged me to do is to come up with a Prisoner's Dilemma-like game to study what happens when the rules are different. For instance, black-white violence in the United States, a large part of that arises from different rules applying to the different populations. And we could do simulations on that to probably confirm what we all already are fairly sure is going on. Okay, and then For this talk, it's sufficient to note that we got very different agents in each of the 4 roles. The question of which choice of roles model what situation is part of the future work. I've got a cute system here. What I've done with it is not too hard, and I really don't know if it even models any situation in the real world, but that's a potential, particularly when I combine it with things like the work that Gary and I are doing on Divide the Dollar, which is an economic game, and of course you could apply it to real games. The other thing is, one of the sort of excessively mathematical things I've done in the past is my students and I invented a numerical signature of how agents play Prisoner's Dilemma, and we needed it because a lot of our research is, well, if you code them with a finite state machine, you get something very different than if you code them with a neural net, which is in turn very different from coding them with a Markov chain. And so what this is I actually fingerprinted the 4 sorts of agents, same color scheme. Red is we want to maximize our score. Green, which is mislabeled, is we want to help A over C. C is we want to maximize our ratio to A, and D is help everybody. And that is a nonlinear projection from 25 dimensions, which is the dimension of the fingerprint I'm using, down to 2. And it shows you, again, the agents were really different from one another, though the type C agents are very similar to the always cooperate agents, which is a little weird. This is why I need to do more analysis if I want to understand. Doing okay for time? Okay, so first of all, Dr. Brown and I are interested in collaboration or simple adoption of the multiple worlds technique. Second, one possible application is non-player characters that are trained to come in with rank R in a free-for-all. So you have 20 populations, say. They're all fighting one another in some sort of first-person shooter simulation. But in each world, the reward is you want to be first place, second place, third place, fourth place, last place. And this will give you a bunch of agents that are pre-adapted to have different levels of competence against one another. So that, I think, might be a nice approach to starting off a dynamic difficulty simulation, because at least you have a bunch of agents that have dynamic capabilities. Another natural direction, and this one's Joey, is if you have somebody who's playing one role in like a fantasy game first-person thing, then you could train NPC, warrior, healer, wizard, and rogue to work well together. That's another thing you might do with this. And then we've played a lot with the self-organizing applications, like the partitioning regression, and Joey's thesis contains extinction and speciation operators. If you've got a population that's trying to capture points to model them and is not capturing very many, you might as well take your most successful population, split it, and drop it into that slot. The people who aren't modeling any points are entitled to die, and the people who are doing a good job of modeling points get to fight with one another and compete to see if they can do a better job or perhaps refine the partition of the points. And so this paper just is sort of pushing the multiple worlds idea, which only Joey and I have been playing with much, though, one thing I'd like during the questions is if anybody has seen somebody else with a parallel approach, I'd like to know about it. And since all the agents were actually using exactly the same data structure in the Prisoner's Dilemma demonstration here, this is a minimal demonstration of the technique. I'd like to thank the money. Any questions? So I meant to ask you during the last thing, when you're asking a question, are you supposed to go walk over to the mic? I am.
Something. So if you go back to your weird line fitting.
3 of them?
No, yeah, no, next. Okay.
That's
so,
not a line.
Yes. Well, some elongated thing, right? Parabola. Do you know the new riddle of induction from Nelson Goodman?
Say again?
The new riddle of induction by Nelson Goodman?
No, I don't.
No. Nelson Goodman argues that Hume wasn't radical enough in identifying the problem with induction, and basically says that. So imagine you have 2 colors, Gru and Bleen, and they define that basically blue is blue before, say, September 27, 2017, and green afterwards, and Bleen is defined the other way around. How do we know that something is green and not, for example, Gru? And he basically says that...
and there's a reason to just not look at light frequencies?
No, but we don't know if this is a thing that will just suddenly change color. And we can't define it as changing color as like more complicated, because that's begging the question. So this is a pretty complicated philosophical argument that has nothing to do with the Computational Intelligence Games Conference, which I find
Thank goodness.
Yes, I find it very fascinating, but this line just made me think of it, because obviously the left hand there seems to be more simple. Right, the left hand fitting, that's right, isn't it?
Yes.
Yeah, but obviously...
The formulas and the numerical hypothesis on the left require far less information to state. That might be a tight way to say what you were saying.
Right, given a particular description language. Right. It just made me think of this. That's and I think it's fascinating, because I don't think it's obvious that the one on the left is better.
Oh, no, you just gave a very short summary of a very long argument after that seminar with my mathematical colleagues. There were half of them were going, the one on the left is obviously right, and the other half was going, no, the reasons the one on the right is superior are long list. It was sort of funny. I didn't even have to talk. I just drank coffee.
And I'm pretty sure it completely parallels the same argument in epistemology.
Well, okay, I'll call this the Grubline slide from now on. Thank you. Lunch?
Yes.
I didn't mean to discourage anyone else from asking a useful question, but...
And, you know, I'm around until Friday lunchtime if you think of questions later.